In this video, we're going to review some information about position versus time graphs and velocity versus time graphs. So let's start by drawing a position versus time graph, a little x versus t. If I have a line on a position versus time graph, then I can take a look at 2 points on that line, and the change in the y, or in this case our x values, would be delta x. We call that our displacement. And the change in these horizontal values would be delta t. So my rise is delta x and my run is delta t. So the slope, or the rise over the run, delta x over delta t, we call that velocity. For a velocity versus time graph, if you have a straight line and you pick 2 points on that line, the change in your horizontal values is the same, delta t, but now the change in your vertical, right, your rise, is delta v, the change of velocity. And we call the slope of change in velocity over a change in time acceleration. So on a position versus time graph, slope tells you velocity. On a velocity versus time graph, the slope tells you about acceleration. We're going to use this to answer a couple of questions about different graphs. From the graph below, find the displacement from 0 to 7 seconds, the velocity at 1, 4, and 6 seconds, and then answer when is the object moving left, right, and at rest. Pause the video and do your best to sketch this graph. Notice that the y values go up by 2 and the x values, or the horizontal values, the times, they go up by 1. All right, let's start with A. The displacement from 0 to 7. Well, at 0 seconds, I can see that I have a position of 4. So I would say x naught is 4. Then here, at 7 seconds, I have a position of 8. So I would say my final position is 8. Now, the displacement, delta x, is x minus x naught. So 8 meters minus 4 meters. And that's going to give me a displacement of 4, which is, if I start here and then I go up here, I have gone up from 4 to 8. So my displacement is 4. All right, B. The velocity at 1, 4, and 6 seconds. So to find the velocity at a time on this graph, so let's start with 1 right here. I just need to find the slope of that straight line, because the slope is the same from 0 to 2 seconds. It's like a constant steepness since it's a straight line. So if I find the slope at any point on that line or between any 2 points on that line, then I can say what the slope at 1 second is. And remember, slope on a position versus time graph is velocity, because the change of x over the change of t. So I just need to pick 2 points on this graph and then divide it by the times. Or we can think rise over run. So I'll pick 0 and 2 seconds. Okay, so my rise, I'm going down 4. So my delta x is negative 4. And my run is a positive 2 seconds. So my velocity is negative 2 meters per second. Okay, at 4, right here, I notice that the line is flat, which means it has a slope of 0, and therefore the velocity at 4 seconds is 0. And you know, a good way to keep track of this is by saying v and then in parentheses putting the time that you're looking at. So for when is it at 4 seconds, we would say 0. And then for 6 seconds, right here, we just need to find the slope of this line. So we can pick any 2 points and use that as our delta x and our delta t. So maybe I'll just, because it's easy, I'll just do from here to here. So the rise is a positive 2 boxes, but remember it's going up from 4 to 8. So that would be plus 4. Plus 4 meters. And then the run just goes over 1 second, so divided by 1 second. So my positive velocity of 4 meters per second. Okay, so part C. If we're trying to figure out when the object is moving left and when it is moving right, we need to look at when the velocity is negative and when the velocity is positive. So I know that in the first velocity we calculated at 1 second, there was a negative slope. So that means from 0 to 2 seconds, the negative slope tells me that the velocity is going left. So left from 0 to 2 seconds. From 2 to 5 seconds, there is a slope of 0, and that tells me that the object is not moving at all. So at rest, from 2 to 5 seconds. And here, from 5 to 7 seconds, there is a positive slope. Right, we calculated +4, so that means it's moving right from that 5 to 7 second time. Great. Let's do another problem. From the graph below, find the acceleration at 2, 4, and 6 seconds. When is the object slowing down, speeding up, or at rest? What position versus time graph would this look like? And what acceleration versus time graph for this, what would it look like? So here we have a velocity versus time graph. Pause the video, take a second to draw this velocity versus time graph. And we have the same scale where the vertical values are going up by 2 and the horizontal are going by 1s. So let's talk about the acceleration at 2, 4, and 6 seconds for part A. Because this is a straight line, then the slope at 2, the slope at 4, and the slope at 6 seconds is all the same. If this line was curving, then the slope would be different at those points. But because it's a straight line, then the slope of the whole line is the same at any point. So to find the acceleration at any of those points, I just need to find the slope of this entire line. So to find the slope of this entire line, the change of velocity over the change of time, I just pick 2 points. And it's such an easy line to figure out that I'm just going to draw a little triangle at the top. It goes down 2, so -2, and again these are meters per second, so the change of velocity is -2, then over 1 second, so the change in time is 1 second. That means the acceleration for this entire line is -2 meters per second squared. Every second this object is changing its velocity by -2 meters per second. Okay, so that's the answer to A. B, when is the object slowing down, speeding up, or at rest? All right, so this one's kind of tricky. Basically, what I'm asking is when do the values of the velocities begin to get closer and closer to 0? Because 0 is where the object is stopped. That would be at 3 seconds. It starts at +6 meters per second, and then goes from +6 to 4 to 0. So that means from 0 to 3 seconds, the object is slowing down. Slowing from 0 to 3 seconds, because it's going from a +6 meters per second to 0. Okay, then it's at rest at 3 seconds, just for a moment. Afterwards, it's going from 0 to -2, -4, -6. The negative doesn't mean less, doesn't mean it's slow. It means left. So the object is now moving left. It's turned around. It was going right when it was in the positive velocities. Now it's in the negative velocities. It's going left, and it's increasing in the magnitude. So 0, 2, 4, 6, 8. That means it's speeding up. So even though there are negative velocities, that still means it's speeding up if it's going away from 0. It's like how you can speed up in your car to the west. Just because you're going west doesn't mean you're slow. So you're speeding up from 3 to 7 seconds. Okay. What would a position versus time graph look like for this? Well, if I sketch a little x versus t graph, I don't really know what position this would start at. I can just sort of pick any position. Let's just say arbitrarily right here. But I do know from this +6 velocity, that I would need to start my line with a slope of positive 6, because slope on a position versus time graph is velocity. So my line would start out at positive 6. But here at 3 seconds, let's mark it right here, I know that I would need to have a velocity of 0, because right here it says I have a velocity of 0. That means my graph, my position, has to somehow be flat, have a slope that's flat at that 3 seconds. Then at 7 seconds, it's negative 8. So somehow there's going to be a negative slope. Okay, well, maybe you can see it from the little tiny dashed lines that I've drawn. This position versus time graph is going to start with a positive slope that decreases constantly until it gets to 0. Then it's going to begin to have negative slope, and it gets more and more negative. So there would be a curved line on the position versus time graph. For the acceleration versus time graph, it's really easy. If I draw acceleration versus time, the slope of velocity versus time, so this graph, tells you what the acceleration is. And the slope for the entire line at 1, 2, 3, 4, 5, 6, 7 seconds, any of it, is negative 2. So my acceleration versus time graph, it is not curving, it's just a flat line at negative 2 meters per second squared. Great. Let's just do one more question. Okay. When is this object slowing down, speeding up, and at rest? So this is kind of like what we just answered before. When you have a curved line on a position versus time graph, the slopes are constantly changing. And remember, slope on a position versus time graph is velocity. So that tells me here at 0 seconds, I can draw a little tangent line there to let me understand what the slope looks like at that point. It's going to be a very negative slope. And then that slope gets less steep and less steep until eventually it reaches 0. So that means that the object is moving to the left from 0 to, let's say that's about 5 seconds. So moving left from 0 to 5 seconds, because the slopes are negative, which means I have a negative velocity, so I'm moving left. And their steepness is decreasing, getting smaller and smaller and smaller, until eventually it's at 0. So 0 means it's stopped. So not only is it moving left from 0 to 5 seconds, it's also slowing down. So it's slowing down from 0 to 5 seconds. After 5 seconds, we begin to have positive velocities that increase. So that means the positive velocities tell you that you move right. So moving right from, this is 5 to 8 seconds. And the fact that that velocity is increasing means, or the steepness is increasing, means that the object is speeding up. Great. That is the end of this video. You have learned how to interpret position versus time and velocity versus time graphs by looking at the slopes of those graphs. You're awesome and fantastic. Congratulations. Yay.